Let's get our head in the clouds with a recipe featured in the new Unity ebook, the Universal Render Pipeline Cookbook, Recipes for Shaders and Visual Effects. See the description below for a free link to the book, and there you'll also find all the resources and assets for this project and the 11 other recipes. If you want to follow along with the video, download the project from GitHub and open it up in your Unity Hub with a 2022 LTS editor version. We'll construct the cloud in 3 stages. First, we'll make a simple sphere within the boundaries of a cube mesh. Then, we'll start using 3D textures to define the shape within the boundaries. And finally, we'll add lighting from the main light. The recipe describes a technique for using ray marching to render a 3D texture. Unity supports 3D textures, which are an array of images placed in a grid on a single texture, rather like a texture atlas, or a sprite sheet. Each image in the array is the same size. Using a 3D UV value, you can source a texel from the grid of images with uv.z, defining the row and column of the image to use, including blending when uv.z finds a position between 2 images. This image shows a typical 3D texture. Note the import settings and the volumetric preview in the inspector. This shader will be built with Shader Graph, and it uses a custom function node. To view the finished product, go to Scenes, Volumetric Clouds, and open the Volumetric Cloud scene. Note that the scene includes a camera, directional light, and a cube. The cube uses the material Raymarch Matte. To start the recipe, you'll need to give the Raymarch Matte material the shader named Shader Graphs Raymarch V1SG, created by Nick Lever. You should now see a sphere. If you adjust the density scale, you can begin to see transparency at the edges. Even though our mesh is a cube, this shader renders a sphere volume, and it does this with a technique called ray marching. For each pixel in the render, we send a ray from the camera to the pixel, and then step along this ray calculating a density. We can use this density to determine the color of the pixel. With this first version, a sphere is defined using a vector 4. XYZ defines the position of the sphere relative to the object, and W is the sphere's radius. For each pixel, a direction is calculated for a ray that shoots directly from the camera. We start by setting a density value to 0. As we travel along the ray, at each marching step inside the sphere, we increment the density by a small amount. When the ray has traveled through the cube, we get a value for how much of the sphere lies directly along the line from the camera to the pixel we're rendering. This density value is then used as the base color in the shader graph. Our shader graph for this uses a custom function node based on the file via scripts, HLSL, raymarch.hlsl. For this version, you'll use the function raymarch v1. The variable density is initialized to 0. Then we enter a for loop for num steps count. The ray origin is moved by step size in the direction defined by ray direction. In order to determine the volumetric density of points in the sphere, we need to know if the current step along the ray origin, is inside the sphere. We can figure this out by using the HLSL distance function, using it to measure the distance from the step position to the sphere's origin. If the calculated distance is less than the sphere's radius, sphere.w, then the density value is incremented by 0.1. The output value, result, then is the accumulated density value scaled or multiplied by density scale. For our calculations, we're working in object space. We get the ray origin using a position node. To get the ray direction, we need a camera node that links the position output to a transform node, with the input set as world and the output set as object. We now have the pixel position and camera position in object space, which enables us to get the ray direction using a subtract node with position as input A and camera position as input B. This ray direction is then normalized using a normalize node. The other inputs to the custom function node are the float properties num steps, the number of marches or steps for each ray, step size, the distance between each step, density scale for giving us control over the overall thickness or opacity of the rendered sphere, and then a vector 4 called sphere, as mentioned before, XYZ for the sphere's position, and W for the radius. The density output goes directly to base color and alpha. Note that this shader is set to be transparent and unlit, so we aren't calculating lighting with this shader. We'll do that in the final step. Ray marching truly comes to life when a 3D texture is added to determine the shape. On the Raymarch material, change the shader to Shader Graphs Raymarch 2SG. Back in the Raymarch shader script, here the custom function used is called Raymarch v2. There are 3 new inputs in the second version of the shader. First, a Unity Texture 3D volume text that comes directly from a material property, a macro sampler texture 3D necessary when working with 3D textures. That needs a sampler state instance. There's a node for sampler state that allows you to select the wrapping option. So set the wrap to clamp so that the UV values outside the range of 0 to 1 are clamped, 0 for values less than 0, and 1 for values above 1. The third input is offset, which is a value we can use to move around our 3D texture inside the cube. This can be useful then for something like fog or the accumulation of smoke high up in an interior. Now, instead of checking whether the ray is marching inside a sphere, we get a sample density value using the float3 sample position of the ray origin step plus an offset. Note that we only need one channel here, the red channel, R. And here's the render of version 2, looking more like a cloud, though sadly without the silver lining. We'll do that next because the final version of the shader introduces lighting. Back to the RayMarch material, change the shader to Shader Graphs RayMarch v3sg. This time we'll use the function RayMarch. This function uses 6 new parameters: numLight steps, light step size, light direction, light absorb, darkness threshold, and transmittance. The function returns a float3 vector called result. To build up the final values, initialize 3 new variables: transmission, light accumulation, and final light. The code is the same as version 2 up to the light loop comment. Let's look again at the ray marching animation we saw earlier. For each step along the view direction ray, we also have a ray shooting towards the main light. The red dots represent the step-by-step sampling of the 3D texture. The more cloud that's found, the less light hits that part of the view direction ray. This process then is determining how bright each pixel is. Back in the light loop, the numLight steps variable specifies the number of times the light loop should repeat. Bear in mind this is a nested loop, and as such there's a performance cost, so keep the numLight steps count as low as possible. The light ray origin vector is set as the sample position and then move towards the main light using minus light direction. When it comes to lighting effects, light direction is generally thought to go from the light source to the object. In this context, we want to move to the light from a point, so that's why we're using the negative light direction to get there. Light density is the density of the light at the current step along the light ray, and this is added to light accumulation. Light transmission is the amount of light that makes it through a volume. That is, how much light passes all the way through without being absorbed or scattered. We need to calculate this outside of the light loop because light transmission is dependent on the total light absorption accumulated throughout all the light steps. As light accumulation increases, it's like more stuff is in the way or the light is being absorbed, and thus light transmission decreases. In order to realistically represent how light interacts with a cloud, we can draw upon mathematical functions that mirror things we observe in the natural world. Euler's number, approximately equal to 2.718, is prevalent in many areas of math like exponential growth or decay patterns. In this context, we can use it to emulate the exponential decrease in light transmission. The reduction in light isn't linear, but exponential. Small increases in stuff in the way of the light result in large decreases of transmitted light. EXP stands for the exponential function Euler's number to the power of. When Euler's number is raised to the power of negative light accumulation, we get a natural emulation of light transmission. A shadow value is calculated next using a property called darkness threshold. Darkness threshold ensures that some level of light is present even in the most shadowed areas. Let's check out the graph for a darkness threshold of 0.15. Note that the shadow value is inverted here, so just think of this graph as light. As light is absorbed, we gradually get less light and more shadow down to the darkness threshold, in this case 0.15. After calculating the shadow value, final light depends on the interaction of 3 factors: the local density of the volume, how much light is able to pass through the volume, the transmittance, and the degree of shadowing. The initial value of transmittance is a property that's passed in. However, with each step through the volume along the view direction, it gets updated and modified by density and light absorption, which determines how much light is lost due to scattering. The result of the function is a float3 containing the final light intensity, transmission, how much light survives after passing through the cloud, and transmittance. Transmittance reflects the cumulative light loss at each step and is carried over to the next step in the ray marching process. Alright, let's check out how we can use this result in the shader graph. Since the output from the custom function is a float3, We're using a split node to use each value separately. Output R, which is final light, goes into a lerp node's T input. Version 3 has several new properties, including color and shadow color. If final light ray march node out.x is 0, then the shadow color will be passed to the lerp node output. If final light is 1, then color is passed to the output. In the range 0 to 1, a linear interpolation of shadow color and color is the output. The lerp node output goes directly to fragment base color. Alpha uses the ray march node with transmission value out.y. This value is 0 when alpha should be 1 and 1 when it should be 0. A 1- node is used to correct the split node B value and link this to fragment alpha. With the shader graph done, let's upload it to the cloud. If you want to make your own custom cloud shapes, there are several ways to create 3D textures like in Houdini. If you use Blender, head over to our YouTube Shorts where we have a workflow tutorial for sculpting clouds in Blender and turning them into 3D textures in Unity. With this volumetric ray marching recipe and the other recipes in the ERP cookbook, we hope you see lots of good things on the horizon.